All right, this is the Unit 2 review, Part 1. I'm going to probably be doing 3 videos to break this up. So we're starting off with, and this kind of jumps back and forth between what's on the calculator part versus what's on the non-calculator part. So notice those are kind of labeled for you. So we're going to look at the first example here of verifying an identity, because we want to try and determine how we would go about doing that. So remember, one of the good things to try and start to do right away is to see if you can write things all in terms of sine and cosine. It won't always help, but sometimes it's a good place to start. So if we look at this and we think about tangent, tangent in terms of sine and cosine would be sine theta over cosine theta. And then plus 2 cosine theta times 1 over sine theta. Okay, so this would be me just looking at this first side. Remember, we don't do anything with the other side. We're going to try to make that look like the other side, though, so maybe we want to get a common denominator. So we'll multiply this side by sine on top and bottom. And on this one, we'll have to multiply top and bottom by cosine. And then I would try to combine this as one fraction. So then we would have sine squared theta plus 2 cosine squared theta over sine theta cosine theta. Now the problem with this is sine squared plus cosine squared would be 1, but this has a 2 in front of it. You can separate that out, though, because remember, x plus x is 2x, so we can separate it out into 2 separate cosine squareds. So this would be sine squared theta plus a cosine squared theta plus another cosine squared theta. So this right here came from the 2 cosine squared thetas. That's where that came from. All over sine theta cosine theta. Okay, well, one of the sine squareds plus cosine squareds would be a 1. So this would end up being 1 plus cosine squared theta on top over sine theta cosine theta. Now, when we look back at the original, what did we want the right side to look like? Notice it was not one big fraction, it was 2 separate terms. So we might want to try to break this back up into 2 separate terms. So since the bottom is a monomial, there's only one thing connected by times down there. There's 2 terms, but they're connected by times. We can split this into 2 separate fractions. And let's see if that gets us where we want to go. So 1 over sine would be cosecant. 1 over cosine would be secant. So cosecant, secant. And then the cosines, one of them would cancel with 1 on bottom, which we get cosine over sine, which is cotangent. So this does match the right side of the one that we started with. So we made the left side look like the right side. Okay, for number 2, we have some things on the side that do not have our typical sine and cosine, so we can try to, and I don't see anything squared, so I don't really see a reason to try to do a Pythagorean identity right away. I'm going to start off by making the cotangent and tangent both terms of sine and cosine. So this first one would be cosine theta over sine theta minus sine theta over cosine theta all over sine theta plus cosine theta. Okay, so if we get a common denominator on top, we'll multiply the first fraction by cosine over cosine. Multiply the second fraction by sine over sine. Still have our bottom. Sorry, sine theta plus cosine theta. Okay, we can combine the fraction on the top. That would be cosine squared theta minus sine squared theta over sine theta cosine theta all over, and I'm going to write this as a fraction now. This is a binomial but we can think of it as being over 1. The reason for that is now I have a fraction over a fraction, so I'm going to take this and make it multiplying by the reciprocal. So cosine squared theta minus sine squared theta over sine theta cosine theta equals, or excuse me, times 1 over sine theta plus cosine theta. Okay? Now, right now that doesn't look like it helps, but this is actually like two perfect squares. You got like an x squared and a y squared. So we can factor that top. So then that would be cosine theta plus sine theta times cosine theta minus sine theta on the top over sine cosine times 1 over sine theta plus cosine theta. Okay, so the sine and cosine theta added together match with that one, just written in a different order. So this ends up being just cosine theta minus sine theta over sine theta cosine theta. Look at your final result. You want cosecant and secant subtracted. So it looks like we need to split this back into two separate fractions. So cosine theta over sine theta cosine theta minus sine theta over sine theta cosine theta. If we reduce, this gives me 1 over sine minus 1 over cosine, and that is cosecant theta minus secant theta. So remember, you're just working on one side and trying to make it look like the other. Okay, let's talk about number 3. So for number 3, I do see some possibilities for Pythagorean identities. We'll have to look through that. It may not work, but let's talk through what we know and what we don't know. Because I know I have some tan squared and secant squareds, I'm going to look at maybe my Pythagorean identities like we said. So remember, sine squared theta plus cosine squared theta equals 1. If we divide all of those by sines, that gives you 1 plus cotangent squared theta equals cosecant squared theta. If you take the original and divide everything by cosine, you get tangent squared theta plus 1 equals secant squared theta. This is the one I think I want to use because tangent squared theta is secant squared theta minus 1. So I'm going to take this top and I'm going to replace the tan squared theta with that statement I just stated. So this is secant squared theta minus 1. Now, this looks like the same thing, kind of, but this has got a squared part. Now, this is perfect squares again on top. So this factors into secant theta plus 1 and secant theta minus 1. The secant theta plus 1s are exactly the same, so those will cancel out. And so we get secant theta minus 1. Now that does not look like this final answer, but secant is related to cosine, so I'm going to try to turn it into cosine. It's 1 over cosine theta minus 1. If we get a common denominator, which means we make the second fraction cosine over cosine, that's where we get the 1 minus cosine theta over cosine theta. There we go. Okay, for the last identity one, we need to look at this statement. We have a fraction that we're trying to turn into just sine and cosine theta. So again, because it's a tangent and cotangent, but I don't see anything squared, I'm going to try to convert things to sine and cosine. So this would be sine theta over cosine theta in the bottom plus cosine theta over sine theta. And this is all over under 1. So then we would take that and try to get a common denominator in the bottom. So I would multiply the first fraction by sine over sine. Kind of seeing a theme here with this. The second fraction I would multiply by cosine over cosine. I would add them together. I would notice that the top of that fraction is a 1 because of Pythagorean identities. And then this is just multiplying by the reciprocal to get that out of the denominator. So 1 times sine theta cosine theta over 1 is just sine theta cosine theta. So that's that one. That one's actually not as bad. Okay, let's look at the next subgroup of problems. We want to find all the exact radian solutions of the equation 2 sine 3 theta plus square root of 2 equals 0. And then we'll have number 6 after that one. So let's talk about 5 first. So we would try to isolate the sine 3 theta first by subtracting over the square root of 2. Then we'll divide by the 2 that's out front. Remember, the 3 inside you can't move. That's part of the argument for the angle. So this is negative square root of 2 over 2. We know that we usually don't solve that as 3 theta, so I'm going to call alpha 3 theta just as a placeholder for right now. So we want to know, when does sine of alpha, this new angle we're calling it, equal negative square root of 2 over 2? So then you have to ask yourself, when does sine equal negative square root of 2 over 2? So hopefully you'll have your unit circle handy, but just remember, sine is all science teachers crazy. Sine is positive in the top two, so it's negative down here. So we're talking about 45-degree angles, because that's when a sine can be a square root of 2 over 2. And this one would be 5 pi over 4, and this one would be 7 pi over 4. Now, that's our alphas. Now, because this is all radians, that means we can keep doing coterminal angles as well. So remember, our way of notating that was 5 pi over 4 plus 2 pi n, where n was an integer, so we could go around either direction of the circle. And then the other alpha would be 7 pi over 4 plus 2 pi n. The problem is that we were never really solving for alpha. We were solving for 3 theta. So we have to replace the alphas back as 3 theta and divide everything by 3. Or if you want to think about it, multiply everything by a third. So this first one would be 5 pi over 12 plus 2/3 pi n. And the second one, so that's my first theta. My second one would be 3 theta equals this. So to multiply everything by 1/3 again to get rid of that 3. This one would be 7 pi over 12 plus 2/3 pi n. So there's my two solution sets that actually are, remember, this represents all possible angles if we just plug in integers for n. So it would give us every single angle possibility that when plugged into this function, multiplied by 3, the answer would be negative square root of 2 over 2 for sine. So that's what we found. Okay, kind of similar situation here for this one, except it's not showing up. Hang on just a second. It's cosine of 4 theta minus pi over 4 equals square root of 3 over 2. So because that inside is all part of the angle, so you notice it's in the parentheses, we're just going to call alpha this time 4 theta minus pi over 4. Okay, so we're going to be solving for alpha first, then we'll back substitute to solve for theta. So this is really just, when does cosine of alpha equal square root of 3 over 2? So again, think to your unit circle. All science teachers crazy. We're going to be a positive cosine, so we're in quads 1 and 4. And square root of 3 over 2 for the x value means that you're going out further this way. And that means this is 1/2. So remember, that is pi over 6. And then the mirror image of that down here, where this would be a negative 1/2. That's negative, remember, 30 degrees. So that is 11 pi over 6. Okay, so remember, we write that alpha, and remember there's all these combinations of those as well. So pi over 6 plus 2 pi n, and the other one is alpha equals 11 pi over 6 plus 2 pi n. That's all the rotations of it. But then we have to remember to back substitute for this big old long 4 theta minus pi over 4. So 4 theta minus pi over 4 equals pi over 6 plus 2 pi n. You want to add the pi over 4 over first, which is going to require us to get a common denominator. So that would be a common denominator of 12. So I'm really doing 2 pi over 12 plus 3 pi over 12. So that's going to be 5 pi over 12. So I have 4 theta equals 5 pi over 12 plus 2 pi n. Then we would multiply everything by 1/4. So theta equals 5 pi over 24 plus 1/2 pi n. So that's my first one. For the next one, we would put in 4 theta minus pi over 4 equals the 11 pi over 6 plus 2 pi n. In other words, remember, we're back substituting here. We add the pi over 4. Okay, this time we would still have a common denominator of 12, but it would be 22 pi over 12 plus 3 pi over 12. So that's going to be 25 pi over 12. So I have 4 theta equals 25 pi over 12 plus 2 pi n, and then we multiply everything by the 1/4 to clear out the 4. So I'm getting that theta is 25 pi over 24. No, sorry. I did the other one wrong. Let me back up. This is a 48. Sorry about that. I was multiplying 4 and 3 in my head, but this is 4 times 12, so over 48 plus pi over 2n. Yeah, so didn't have an eraser there, but those are both 48s, not 24s. Sorry about that. So yeah, when we multiply by the 1/4, you're doing 12 times 4, not 4 times 3. So it is 48. Okay, for number 7 and 8, we are finding the exact solutions of the equations that are in the interval 0 to 2 pi. If I actually try to enter and put in a space here, it makes some of this go away, so I'm just going to rewrite this. So this is 2 minus 8 cosine squared theta equals 0. We could factor a 2 out of that, and that would be 1 minus 4 cosine squared theta equals 0. We could factor that again, because that's 2 perfect squares. This would be 1 minus 2 cosine theta and 1 plus 2 cosine theta. So if we set these equal to 0 and solve them, now the 2 doesn't give me any solutions because it doesn't have a theta on it. But this one will give me positive 1/2 because I would subtract and then divide by negative 2. And this one I would subtract 1 and then divide by positive 2. So I get negative 1/2. So we're looking for the locations where cosine equals 1/2 and cosine equals negative 1/2. So if we think about our group here, and we don't need to do any back substituting this time. Notice there's nothing in there except for a theta. So we're just solving these for the theta. So remember, for cosine to be 1/2, the x value has to be 1/2. So that means your triangle has a 1/2 and then a square root of 3 over 2. And for it to be positive, you're going to be in these two quadrants. So this is for the cosine theta equals 1/2. And this would be the angle pi over 3, and this would be the angle, let's see, that would be, oh, my brain just stopped for a second. This is 4 pi over 3 over here. This would be 5 pi over 3. Okay, so for this one right here, we get pi over 3 and 5 pi over 3. For the negative 1/2, we get the other two images of cosine. And they're still going to be related to pi's over 3 because it is still the 1/2. But this time, this one will be 2 pi over 3, and this one will be 4 pi over 3. Now, if you're writing them in one big blank, you would probably write them from least to greatest. So pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Okay, let's talk about number 8. So this one is 2 sine squared theta equals 1 minus sine theta. I would try to get everything on one side because this sort of looks like maybe a quadratic. So let's add that sine over and then subtract the 1 over so that everything's on the same side together. And then try to think of this like factoring x squared, 2x squared plus x minus 1. That's really what we're factoring here, except our x is a sine theta. So we would do 2 times negative 1, which is negative 2, And it looks like the middle, we would split this into 2x and minus 1x if we're doing factor by grouping. So this would be 2x, x plus 1, and minus 1, x plus 1. So this factors into an x plus 1 and a 2x minus 1. So remember, we're going to use sine instead of x. So sine theta plus 1 and 2 sine theta minus 1. Set them both equal to 0. This would be negative 1, and this one would be add 1 divide by 2, so 1/2. Okay, so we need to think, where is sine of theta equal to negative 1? So for sine to be negative 1, remember that means the y value is negative 1. That only happens in one location, because this would be 0, positive 1. So 3 pi over 2 is the only solution from 0 to 2 pi that gives the answer of negative 1 for y. For sine of 1/2, remember that's going to be positive, so all science, so we're in these two quadrants. That means that your y value is 1/2. That means we're talking about the angle of pi over 6, because it's the 30-degree angle. And we'd have another one over here, and this one would be 5 pi over 6. So this theta gives me pi over 6 and 5 pi over 6. All right, let's look at number 9. This is asking us to verify some identities. We can use what we know about the addition and subtraction formulas for sine and cosine and tangent to do this. So if we have sine of a theta minus pi over 2, this is the subtraction formula for sine. So remember, sine is social and agreeable. So that means the sine and cosine stay together as a group. So sine, cosine, they mix together, and then we actually keep the sign. So this is negative, and then we would have cosine of the theta and then sine of the pi over 2. So notice each one has a different sine or cosine angle. So this is just working out the cosine and sine of pi over 2. Remember, pi over 2 is the point 0, 1. So the cosine is 0. So that means this is just sine theta times 0. And this is negative cosine theta times 1. So 0 times anything is 0. That just makes this negative cosine theta. So there's the proof for that one. For the addition formula for cosine, remember, we are antisocial and disagreeable. Sorry, this doesn't want to stay on the spot that I'm trying to be. That means that cosines and sines do not mix together. So cosines stay together and sines stay together, and we change the sign in the middle for the cosine formulas. So cosine theta plus 3 pi over 2 is cosine of theta cosine of 3 pi over 2 plus, minus, because we're disagreeable, and then it would be sine of theta sine of 3 pi over 2. So let's think about where 3 pi over 2 is. That's down here on the unit circle. That's the ordered pair 0, negative 1. So cosine is 0 again of the 3 pi over 2. The sine is negative 1. So this actually ends up being 0 for the first part, and then negative times negative is positive sine theta. So there's that one. Tangent's formula is a little bit harder. Remember, it stays exactly as it is on top, but it's we keep the sign. So it would be tan of the theta plus tan of the pi over 1 minus the two tans together. Now the bottom will always be the opposite sign of whatever's here. So if this had been a minus, this would have been a plus down here. So let's talk about tan of pi. So remember, pi is the point negative 1 comma 0. When you do tangent of pi, that is 0 over negative 1, which is 0. So this is actually tan theta plus 0 over 1 minus tan theta times 0. So that ends up just being tan theta, because the top is tan theta and the bottom ends up just being 1 because of the times 0 down here. So those aren't too bad. All right, so let's look at number 12. So we're going to try to get to at least number 14 before I cut off this first video. So for number 12, it says use the given conditions to find the exact values of the expressions. So we're looking at what information they've provided us with, and we're going to draw what we know. They've said cosine theta is 24 over 25. Notice that's a positive cosine, but they told me cotangent is less than 0. We need this to figure out our quadrant. So if cotangent is less than 0, that means the tan theta is also negative. Remember, tangent's the family for cotangent. So then we're looking at a quadrant where we know that cosines are positives but tans are negatives. That puts us down here in quad 4. Okay. Now once we get that quadrant, we can then label our triangle using this cosine part. So cosine is adjacent over hype, so that's 24 over 25 is the hype. So we need to find this other side, and I believe it's 7. I don't have a lot of room to write, but we're going to double check. The hypotenuse is 25 squared, and then minus 24 squared for the leg. That gives me 49, so square root of 49 is 7. So this is 7 by Pythagorean theorem. So I now know that if I have this, I can find my sine theta and my tangent theta if I need them as well. And this is negative, by the way. I did not mark that. That's why the quadrant mattered. You needed to know if the missing leg was going to be positive or negative. So since that's negative, the sine is negative 7 over 25. And the tangent theta, even though we don't really need it for this problem, is opposite over adjacent, so that's negative 7 over 24. Now what they want us to actually do is sine of theta plus pi over 6. So we know pi over 6, but our theta is related to this triangle we've drawn. So remember, sine is social and agreeable. So sine theta mixes with cosine of pi over 6. Agreeable means we keep our sign. And then cosine of theta is going to mix with sine of pi over 6. Okay, so sine of theta we now know. It's negative 7 over 25. Cosine of pi over 6, remember pi over 6 is just one of our unit circle values. So remember pi over 6 is 30 degrees, which means that's 1/2 square root of 3 over 2 and 1. So if you're looking at cosine of that, that's going to be the square root of 3 over 2. Plus cosine of my theta they gave me at the beginning is 24 over 25, and sine of pi over 6 is 1/2. If we work this out, this is negative 7 square root of 3 plus 24 all over 50, because both denominators are exactly the same. So there's number 12. Okay, let's look at number 13. This is tan theta equals negative 5 over 12, and sine theta is greater than 0. So sine is positive and tan is negative. So we need to get the right quadrant for this. So all science teachers crazy. For tangent to be negative, you can't be in 1 or 3. Sine is positive, so we have to be in 2. And then this is our theta, and then they told us that tangents 5 and 12, we can figure out the sign by what quadrant we're in. The x's are negative over here. So that's why it's a negative fraction. So this is 5 and negative 12, and then that would be 25 plus 144. Because those are both legs, which is 169. So that means this is positive 13. Hypotenuse is always positive. So then we've got to do the cosine subtraction formula. So cosine theta minus pi over 3 is, remember, antisocial and disagreeable. So cosines are going to stick together like glue. Disagreeable means we're going to change the sign in between them. And the signs are sticking together. Okay, now we also need to find our information over here. So cosine of theta is negative 12 over 13. That's the part we're missing because we have, well, we also need sine of theta. They gave us tangent. So sine of theta is 5 over 13. There we go. So cosine would be negative 12 over 13. This, remember, is just cosine of pi over 3. So pi over 3, remember, is a 60-degree angle. 60 degree, you have square root of 3 over 2, then 1/2, then 1. So cosine is 1/2 here. Sine of theta is 5 over 13. And sine of pi over 3 is square root of 3 over 2. So this is negative 12 plus 5 square root of 3, and they're both over 26 because 2 times 13. Okay. All right, so let's look at this next one. Number 14 is cosecant is negative 17 over 8. You might want to rewrite that as sine of theta is negative 8 over 17. That's usually more useful. So sine is negative. Secant, which is really in the cosine family, is positive. And then they want us to do the tangent formula. So let's figure out where our theta is. So we need a place where sine is negative but cosine is positive. So sine is negative down here in both of these, but cosine is positive in quadrant 4. And then we've got sine, so that is 8 over 17, and the 8 is the negative part since this is quad 4. So that would be, off the top of my head, I don't know, 17 squared minus 8 squared is 64. That's 225, and the square root of that is 15. So this other leg is 15. So that means that my cosine of theta is 15 over 17, and my tan of theta, which is what I'm really going to need, is going to be opposite over adjacent, so negative 8 over 15. So in the tan formula, we have theta minus pi over 4. That means we're doing tan of theta minus tan of pi over 4. Over 1 plus, because we changed signs on the bottom, tan of theta times tan of pi over 4. Okay, so tan of theta is negative 8 over 15. Tan of pi over 4, remember that's a 45-degree angle. And in a 45-degree angle, you have square root of 2 over 2, square root of 2 over 2, and 1. Tangent's always 1 here, so this is going to be minus 1 over 1 plus negative 8 over 15 times 1. On top, I would make that 15 over 15, so I can get a common denominator. So that would be negative 23 over 15. On bottom, I'd do the same thing, make this 15 over 15, but this time we're subtracting 8 since times 1 does nothing. So that'd be 7 over 15. And when we multiply by the reciprocal, we get negative 23 over 7. So there's the answer to that one. And that is where I'm going to stop the first video, and I'll pick up with number 15 on part 2.